In this video, we are going to do a couple examples where we try to find both the local maxima and local minima of a function, as well as the absolute maxima and the absolute minima of a function, if they exist. Let's start by just reminding ourselves of some of the definitions. So here is the textbook definition of a local maximum or minimum. And if you'd like, you can pause this and read through this. But I'm going to, instead of going through the textbook definition, I'm going to just start by going over a more intuitive understanding of what a local maximum or minimum is. So a relative maximum often looks like the point at the top of a hill, as we see on this picture on the left. A relative minimum, on the other hand, is more like the point at the bottom of an alley, of a valley in the graph of a function. Okay, I think that's a little bit easier way of understanding it more intuitively what a local maximum or a local minimum is. And it doesn't need to be the biggest possible hill. It could be a small hill that you see in the function, and maybe other points are larger or smaller than that point. Or with a local minimum, maybe there are other points in that on that function that are actually have a smaller y value, but nonetheless, as long as it is the smallest or the highest point compared to the other points that are near it, then that could be a local maximum or a local minimum. One thing that is important is that in order for a point to be a local maximum or a local minimum, there must be a continuous curve of points in the graph of the function to the left and to the right of that point connected to that point. Next, there's absolute maximum, absolute minimum. Again, here is the textbook definition. Feel free to pause and read this, but I'm going to explain it a little bit more intuitively. Intuitively speaking, the absolute maximum of a function is the output of f of x that is greater than or equal to every other output of f of x, if such a value exists. Similarly, the absolute minimum of a function, f of x, is the output of f of x that is less than or equal to every other output of f of x, if such a value exists. So unlike a local maximum or minimum, it is not required that an absolute maximum or minimum has a continuous curve of points to the left and to the right of that point that is connected to that point. All right, so we'll start with these examples right here. And I like finding the absolute maxima and the absolute minimum first because I find them a little bit easier. You're just trying to find what point is the highest point in this function, or what's the lowest point in this function. Notice that we have an arrow right here. That means that this graph is going to keep going up and up and up to infinity. That means that there is no absolute maximum. Similarly, since we have this arrow pointing downwards, this graph, as x gets larger and larger, y is going to keep going further and further. It's going to get smaller and smaller, which means that there is no point that's lower than every other point. There is no absolute minimum. If a graph goes to either positive infinity or negative infinity, that means if it goes to positive infinity, there will be no absolute maximum. And if it goes to negative infinity, there will be no absolute minimum. And in this case, there's both. So we have no absolute maximum nor any absolute minimum. We do have, however, a local maximum and a local minimum. the way I look for these, I look for either hills or valleys. I'm going to start with my hill. Do you see there's a small hill right here? And so that point at the top of the hill is a local minimum. So a local maximum. There's a local maximum at, and it looks like it is -1, 7. Now, that's the coordinate. You could also say that the local maximum has a value of 7. We'll say the local maximum is 7. That y value is actually what the local maximum is. There's also, in this case, a valley. If you look right here, we have our valley, and so that point right there is a local minimum. So we have a local minimum at, and I think that the coordinates there are -3, +3, and so that means that the local minimum is 3. And again, notice it is very important that you're able to trace numbers to the left and to the right of your local maximum and your local minimums, and we are able to do that. All right, let's look at the next one. Is there an absolute maximum? Is there a maximum value that this graph achieves? I would say yes. So there is a when I said there's an absolute maximum, so there is an absolute maximum. And that is at 0, 2. And that's where the absolute maximum occurs. The absolute maximum of the function is 2, right? That's the largest possible number. That's the largest possible output of this function. One thing I want to point out too is that notice I have my little hill right here. 2 is also a local maximum. In this case, okay? So sometimes your absolute maximum could be a local maximum as well. How about minimums? Well, this is a kind of interesting function because this function is actually asymptotic. As this function goes to positive infinity and negative infinity, as the x values go to positive and negative infinity, the y values get closer and closer to the x-axis, which is the line y equals 0. But it gets closer and closer, but it never touches the x-axis. So the numbers get closer and closer to 0, but they never actually, the function never is equal to 0. So maybe somewhere as you go out, it's 0.01, my output, my y value. Maybe for a bigger x value, it's 0.00001. Maybe for a very, very large x value, it's 0.000000001. It'll get closer and closer, but it'll never quite get there. For that reason, there is no absolute minimum, right? There's always a smaller number there's always a smaller y value for every x as the x value gets bigger. So there's no absolute, and indeed there's no valley either, right, that we can see. It's not going to turn back up. It keeps getting smaller and smaller. So there's no absolute nor local minimum. in this for this function. All right, let's do two more examples. I'm going to copy and paste this over to OneNote. All right. And for these, at least for number 13, I'm just going to label these points. I'm not going to write down in full sentences like I did in the previous example. But let's go ahead and get started. All right, let's start with absolute maximum. The absolute maximum, notice this arrow. This is telling me that this function is just going to keep going up, up, and up. So there is no absolute maximum. But are there any local maximum? Again, the way I think about this, I look for hills. Do I see any hills? I see a hill right here, and I see a hill right there. So I would say that both of these are local maxima. And when we say maximum, that's one. The plural would be maxima, as opposed to maximums. Next, let's do absolute minimums. Is there a y value that is smaller than every other y value in this function? I would say yes. This point right here is an absolute minimum. It is the smallest y value possible at 0, 1, and the absolute minimum is 1 in this function. Are there any, let's see, local minima? Again, I'm going to look for my valleys and see if I can trace a U. Here, I can trace a U right there. So this point would be a local minimum. But there's more than that. We have another valley right there. And so these two are both local minima. Notice that this is not a local minima right here. That would be incorrect to say that's a local minima. And the reason why is I cannot make a U there. There are points to the right of that point, but there are no points to the left, right? So if I have something that looks like this and it ends right here, that can't be a local minimum. Now if I had just even a little bit more, and I can actually trace a U around it, or a V, then that would be a local minima. But again, as I said earlier, for local minima, you must have points to the left and the right, and it has to be continuous. You need a continuous curve that contains your local minima with points to the left and to the right of that local minima. All right, so I think that's pretty much it. Let's do the last one. All right, any absolute maximum? Well, we have an arrow going up, so no, and same with this arrow going down tells me that there's no absolute minimum either. So there's no absolute maximum or minimum. Again, and if I look at this, are there any hills or valleys? Not really. This almost looks like a hill, right? But it's like a kind of a diagonal hill. And it's not like this point is at the top of the hill, right? In fact, this point just keeps getting closer and closer to the x-axis. But again, it's not a hill. It never goes back down. If this graph kept getting closer and then eventually turned down, then you could say, yes, there's a local maximum somewhere over there. But again, this graph is asymptotic to the x-axis. So there's actually, in this case, no local minimum nor is there any local maximum. All right, so hopefully those examples helped, and we will see you in the next video.